Hey, hi and welcome back. Now let's start with this video which is about system power budget calculation. So you already know what you are going to learn in this video. We are going to discuss the process to calculate the power budget, and power budget calculation is actually nothing but in this process we calculate the total current consumption of the system, and also we finalize the voltage or voltages at which our system is going to work. So I will show you the detailed procedure to calculate the total current consumption of the system, and also I will show you how to finalize the voltage or voltages for the system. Okay, so that's how basically we are going to cover this video, and I'm sure you will definitely enjoy this power budget calculation process. Alright, so now let's start with this video. So what is power budget? So quickly I will give you the definition of power budget. It is basically the power utilization and power consumption calculation associated with the system. Okay, and same thing we are actually going to do in our case. We are going to do the power consumption calculation for our system. Alright, so now let's start with the process to calculate the power budget. So this is basically the block diagram of our hardware, and we have already discussed this particular block diagram in detail. But here if you see, I have done some minute changes in this block diagram. So you can see there are actually some small extra lines which are actually shown in orange color and red color. Okay, so these lines are basically the power lines, and from their path you will actually understand to which blocks they are actually delivering the power. So orange line, which is actually the output of this power supply, it's delivering the power to this microcontroller block, then this motor driver block, then this binary to BCD decoder block, and after that switch input and potentiometer block. So these are the blocks which are actually powered from the output of power supply. Okay, and this RGB block that you see, it's actually not powered by the power supply. Instead of that, it's actually going to take the power from the microcontroller. Okay, so when we will discuss the RGB topic, at that time you will actually understand how it's taking power from the microcontroller. Okay, so at this moment you don't need to bother about this RGB block. After that, I hope you remember I told you we are actually going to power our hardware or our system using an external 12 volt adapter or using an external 12 volt power supply. Okay, so if you see here, this 12 volt line is actually provided as an input to this system power supply, and also it is provided as an input to this motor driver block. So this motor driver block is actually going to take power from the output of system power supply, and also it's going to take power from the external power supply. Okay, the reason is one power supply is actually used for the internal operation of the IC, and another power source is actually used to drive the motors which are actually connected to this motor driver IC. Okay, so I hope that this particular point is clear now, and also I hope that now it's clear how the different blocks are powered. Okay, now let's do the power budget calculation. So I told you to do the power budget calculation, we actually need to calculate the total amount of current which is actually consumed by that particular system. Okay, now in this block diagram you will observe that beside every block I have actually written its operating voltage and the total amount of current which that particular block is consuming. Okay, so now let's try to understand how these values of voltage and current came. Now let's start with this block, which is basically microcontroller block, and we have already discussed that we are actually going to use a Atmega 328 microcontroller. And you know, whenever you have to calculate or whenever you have to get the maximum current consumption value for a specific IC, at that time you have to go to the datasheet of that particular IC, and in the datasheet of that IC you will actually find one section which is called as electrical characteristic section. And in the electrical characteristic section it will be given what's the maximum amount of current that particular IC is going to consume. In the same way you have to go to the datasheet of Atmega 328 microcontroller, and in the datasheet of Atmega 328 microcontroller you will find the electrical characteristic section, and in that particular section you will get to know what's the maximum amount of current the Atmega 328 microcontroller is going to consume. Okay, so this 300 milliampere value, it actually came from the electrical characteristic section of the Atmega 328 microcontroller's datasheet. So in the same way, for different blocks you have to actually refer the data sheet of the ICs, and in the electrical characteristics section of their respective data sheet, you will find what maximum amount of current those ICs are actually draining. Okay, so I will put the image of electrical characteristics section of Atmega 328 microcontroller, and there you will find the maximum current which this particular controller or Atmega 328 controller is draining. It's basically 300 milliampere. So this controller is actually draining 300 milliampere. It does not mean all the time the controller is actually going to drain this particular value. It actually depends on application which the controller is executing, or how many pins of the controller are actually used during the operation. So based on the number of pins, then based on the mode of operation of the controller, it will be decided how much current this particular controller is going to consume. And this 300 milliampere value, it's basically the maximum current value which this controller is going to drain. Okay, and it will never drain the current more than this particular value. So I hope that it's clear now. After that, again, this particular value which is 5 volt, which is basically the operating voltage of Atmega 328 microcontroller, and we are actually going to provide 5 volt for its proper operation. And again, this particular value came from the data sheet. So you have to go to the data sheet of Atmega 328 microcontroller, and again in electrical characteristics section, it will be given what's basically the operating voltage range for the Atmega 328 microcontroller. So Atmega 328 microcontroller can work on 2.7 volt to 5.5 volt. And we are actually using this particular voltage, which is basically the standard voltage, whenever we use the power supply. So we are actually going to provide 5 volt to the Atmega 328 microcontroller for its proper operation. You can also use 3.3 volt. Again, 3.3 volt is also a standard voltage, when it comes to power supply. But if we use a 3.3 volt, then we will have to design two different power supply. One power supply will produce 5 volt and another power supply will produce 3.3 volt. So unnecessary, it's going to increase the size of the PCB, and along with that, it's going to increase the bill of material cost. Okay, or it's going to increase the price of the PCB. Okay, because the number of components will actually increase. That's the reason. That's actually one of the reason why we are using 5 volt power supply to power the microcontroller. Okay, otherwise you can also use 3.3 volt to power the microcontroller. And another reason is rest of the blocks are also going to work on 5 volt. So that's basically another reason why we are using 5 volt to power the microcontroller. So 5 volt is going to be the operating voltage of the controller, and 300 milliampere, it's going to be the maximum current which this particular controller is going to drain. So the maximum power this controller block can drain, it's basically power is equal to Vi. So 5 into 300 milliampere, which gives us 1.5 watt. So 1.5 watt is basically the power which this controller block can drain. So that's basically the power budget calculation for the controller. In the same way, we are going to do for motor driver section also. So in case of motor driver section, there are actually two power supply. The one is directly coming from the output side of this power supply, and one is actually coming from the external adapter or external power source. And again here I have given the voltage and a voltage and current rating for one power supply and voltage and current rating for another power supply. So this motor driver block is actually nothing but a motor driver IC. And in motor driver IC, there are actually two pins to power the IC. The first one is VCC1 and the second one is VCC2. Okay, so these are basically two pins through which this particular IC consumes the power. And in the data sheet of this motor driver IC, again, you have to go to the electrical characteristics section. So you will find that the voltage range for the VCC1 pin, it's basically 4.5 volt to I think 5.5 volt. And we are actually using 5 volt to power the VCC pin because the 5 volt lies between this particular range. And again, if you check the electrical characteristics section, the maximum current that this particular IC can drain from this VCC pin, it's actually 60 milliampere. And that's how this value of 60 milliampere came. So VCC pin to VCC pin, we are actually going to provide 5 volt, and the maximum current which this particular IC can drain from the VCC1 pin, it's basically 60 milliampere. After that, in case of VCC2 pin, if you go to the data sheet, you will find that the maximum voltage that you can provide to this particular pin, it's actually 36 volt. But we are not providing 36 volt to the VCC2 pin. we are actually providing 12 volt to the VCC2 pin. The reason is the motors that we have connected to this motor driver IC, they are actually going to work on 12 volt. That's the reason instead of providing 36 volt, we are actually providing 12 volt to this VCC2 pin, okay? But it's up to you. You can also increase this particular voltage. You can also provide 15 volt to the motors. But here we have to, change the power supply source, okay? So that you have to remember. So here I want this motor to operate at 12 volt. That's the reason I'm actually going to provide VCC2 with the 12 volt power supply. And again, if you check the datasheet, you will find that this particular pin can drain maximum current of 600 milliamperes. So we can drain maximum current of 600 milliampere from this particular pin at 36 volt. So if you observe, if we do the power calculation, power is equal to Vm. So if I do the power calculation, then the voltage into current, that gives us 21.6 watt. Okay. So that's basically the maximum amount of power that we can drain from this particular pin. But as we are using 12 volt to power this particular pin, so in our case, the maximum current that we can drain from this particular pin is going to be different. So as per data sheet, the maximum power that we can drain from this particular pin, it's actually 21.6 watt, right? So if I substitute the value of voltage that we are using, which is basically 12 volt, so that gives us I is equal to 1.8 ampere. So that's basically the maximum amount of current that we can drain at 12 volt from this particular pin. But when I practically checked the operation of motor, I found that the maximum current which these motors that we are going to connect to the motor driver IC, they are actually going to consume the current less than 50 milliampere. That's the reason I have considered this particular value 100 milliampere. Okay, so we don't have to bother about this particular value or this particular value, because we have practically checked the motors are actually going to drain the current up to 50 milliampere. So I have actually slightly increased the current consumption value, which is 100 milliampere for the safety, and we are going to consider this particular value in our power budget calculation. In the same way, you have to go to the data sheet of binary to BCD decoder, and there you will find that this particular IC can work at 5 volt, and the maximum current that this particular IC can drain, it's basically 60 milliampere. Okay. In the same way, for switch input, whenever we use a switch, it's not going to drain much current. It's going to be less than 1 milliampere. So when we will discuss the switch topic, at that time we will do the detailed calculation. But at this moment, just consider that the switch is actually going to consume the current less than 1 milliampere. In the same way, this potentiometer is actually going to consume current less than 1 milliampere. Okay, and both the blocks are actually going to work on 5 volt. And we are not doing the power budget calculation for the RGB LED because the current consumption of this particular block is already included in this particular value 300 milliampere, because this block is actually going to consume the current from the microcontroller, and it's not going to consume the current from the power supply. That's why we are actually excluding the current consumption of this RGB LED here, because it's already included in this particular value. So we are done with all these blocks. Now we are just left with this particular block, and this particular block is actually nothing but the male headers on our PCB. So I will put the image how exactly the male headers look like. So these programmer debugger block is actually just the male headers, and to these headers we are actually going to connect an external hardware, but that hardware will be actually connected to the computer. Okay, it's actually going to consume the power from the USB port of our computer. So we are not going to consider the power consumption of this external hardware in our power budget calculation. So we will exclude that part. Okay. So now let's calculate the total current consumption. So this particular microcontroller is going to drain 300 milliampere. Then motor driver block is going to drain 60 milliampere. So that becomes 360 milliampere. Then this 60 milliampere, that becomes 420 milliampere. And then these 2 milliamperes, okay, 1 milliampere and 1 milliampere. So total current consumption, it's actually going to be 422 milliampere at 5 volt. So the power supply IC or the power supply block that we are going to design, it has to provide 5 volt on the output side, and that power supply block should be capable to provide 422 milliampere for the proper operation of all these blocks. Okay, and if this power supply block provides the current less than this 422 milliampere, then our system or all these blocks or any of the block might not work. That's the reason we have to design the power supply block in such a way that it should provide 5 volt on the output side, and also it should be capable of delivering 422 milliampere. So these numbers are actually telling us that we have to design a power supply block which will provide 5 volt on the output side, and that power supply block or that power supply circuitry should provide current more than 422 milliampere. So you can select the power supply IC that can deliver current like 500 milliampere or 1 ampere or 1.5 ampere. Okay, so you can select the IC accordingly. After that, now let's do the output power calculation for this power supply block. So we can write power as VI. So we have the output voltage as 5 volt. So 5 into and then the output current, it's going to be 422 milliampere. So I can write 0.422. So that gives us output power as 2.11 watt, which I have written here. So this is basically the power which this power supply block has to deliver on the output side for the proper operation of all these blocks. Okay. Now let's calculate the input power considering this output power. Now here the IC that we are actually using, it's basically a linear regulator IC. Okay. And generally, the linear regulator ICs have the efficiency of, 50 or 60%. So what we are doing, we are actually considering the efficiency of 50%, which is actually the decent value. So what exactly that means, if there is a X input power, then we are just going to get X by 2 power on the output side. And rest of the power, it will actually, it will get lost in the power supply IC, because the linear regulators have the lower efficiency. That's the reason there will be power dissipation. Okay. So let's consider the X as an input power, and let's consider the efficiency as 50%. And considering that, let's calculate the input power. So as I told you, we have the efficiency of 50%. So X into 50%, that gives us the output power of 2.11 watt. Okay. And that gives us input power as 4.22 watt. So that will be the input power. So when we will provide 4.22 watts of input power to this particular power supply IC, then this power supply IC will be able to provide 2.11 watt of output power. And with this power, let's calculate the input current now. So again, we will use the same formula, power is equal to VI. And we already know the input power as 4.22. And also we are actually going to provide the 12 volt input to this particular power supply IC. So 4.22 divided by 12, that gives us the current value of 351 milliampere. Okay, which actually I have written here. So in order to deliver the output power of 2.11 watt, we have to provide this particular power on the input side, and this is going to be the input current value. So 350 milliampere will be consumed by this particular power supply IC. Then this 100 milliampere will be consumed by this motor driver IC, and this value of current is actually at 12 volt. Okay. So the power supply or the external power supply or the external adapter that we are going to use to power our system, it should be capable of providing 12 volt on the output side, and it should deliver maximum current of 451 milliampere. So that's basically the current which this particular power supply should deliver. Okay. So if you are using an external adapter, then generally, in market, the adapters with 12 volt 500 milliampere rating are standard. So you can also use that particular adapter to power our system, because this 500 milliampere value is greater than, the current requirement of our systems. So the adapter with this particular specification is actually more than enough to power our system. Or you can also use an adapter with 12 volt 1 ampere rating. Again, this is basically the standard adapter specification. So again, you can use this adapter to power the system. So from this power budget calculation, we are actually getting two conclusions. The first one is the power supply block that we are going to design, it should provide 5 volt on the output side, and it should be capable of delivering current more than 422 milliampere. Okay, so that's basically the first conclusion. Then the second conclusion is the power source that we are using to power our hardware, it has to provide 12 volt on the input side, and it should be capable of delivering 451 milliampere. Okay, 451 milliampere. So considering these 2 points we have to design the power supply block, or we have to choose a IC which can provide 5 volt on the output side by taking the 12 volt from the input side, and it should be capable of delivering this much current on the output side. So that was all about the power budget calculation. I hope that every single thing that we discussed in this video is now crystal clear to you. And if you still have any kind of doubt, then do not hesitate to ask question. Okay, so ask me the questions and I will help you with that. Alright, so that's what I wanted to tell in this video. Now I will see you in the next video, which is about introduction to power supply IC. Okay, so I will see you in the next video now.